So the test that we saw in our last class period was really a chi-square test of independence, where we had a single sample from which we were drawing our data, and we're testing to see if the distribution of those values across our sample is what we would expect if that null hypothesis is true and there really is no relationship. Remember that our expectation was derived from our equation for independence. We had, if we're doing this by hand, expected count or expected value is equal to row total times column total divided by overall total. So in our example from the previous class period, we were looking at the young adults, ages 19, 20, 21, and 22, and their living arrangements, living with their parents, living with roommates, living on their own, group home, etc. And we were seeing if those are truly independent of one another, meaning that the age has no impact on that living arrangement. We calculated what we would expect that distribution to look like based off of the overall total. And the whole process of the test was comparing what we observed to what we would expect. In each of those cells on a table, and some of them have bigger differences than others, what the chi-square does is it looks at the big picture. And it determines if our chi-square test statistic is large enough, that corresponds with a p-value that's really small. Same interpretation of p-values that we've had the entire year. Small p-value, reject the null hypothesis, accept the alternative. We do have a significant relationship between these variables. That was a test for independence. The key when using that test is if you're drawing data from a single sample. A single sample representing a single population. The other test that we're going to use today is called a chi-square test for homogeneity. Now, with this, you're comparing two different samples from two different populations. So you're no longer looking to see if they're independent of one another. Instead, you have one variable from a sample that you've collected, and you're looking at its breakdown of the variables. You also have a different sample's data, and you're looking to see if that breakdown is proportional to what you would expect in the other group. Okay? So we have this here. Okay? It says for each sample we classify individuals according to one variable, and we are interested in whether or not the probabilities of being classified in each category of this variable are the same for each population. In this context, our calculations for the chi-square test are unchanged, but the method of collecting the data is different. Okay, so our procedures are going to be the same. Nothing new in that front. The only new aspect of this, instead of everything coming from a single sample and they are placed into that 19-year-old, 20-year-old, 21, 22-year-old category, now the two samples that we have obtained, they have that distinguishing characteristic that separates them. So we take the samples separately. We're testing to see if the distribution is the same. So this is referred to as a chi-square test for homogeneity, since we are interested in whether or not the two populations from which the samples are selected are homogeneous or homogeneous, whichever pronunciation you want. Okay? Meaning the same. Do they come from the same population, even though they were obtained separately? Okay? With respect to that classification variable. All right, enough behind the scenes stuff here. Let's essentially the same thing. Setting up the hypothesis. Okay, still talking about no relationship or a relationship. All right, let's look at an example here to illustrate this test of homogeneity. The background here says random digit dialing telephone surveys do not call cell phone numbers. Okay? There are restrictions on that. Legally, they are not allowed to call cell phone numbers. Now, you still get like spam calls and stuff because they are not actually legal calls. But we know that cell-only users tend to be younger, which results in younger adults being underrepresented in a random digit dialing sample. So they've been trying to overcome that sampling issue for years. Survey organizations can compensate for this by weighting the younger adults in the random digit dialing sample more heavily, but this assumes that the young adults accessible by landline are similar on the survey issue to their cell-only peers who are excluded. Okay? So their idea of how to overcompensate for this, not overcompensate, to compensate for it, is to weight the landline young adults that they do reach more heavily. However, are those landline young adults the same in their attributes as those that they would see in the cell phone sample? You see this formulating here. We have two distinct populations. We have the cell phone only young adults, and we have the landline using young adults. And we're testing to see if they are essentially the same grouping, they are homogeneous, or are these differences so clear that there is a relationship between which categorization they fall into and, in this case, their living situation. So, in young adults between 18 and 25 years of age, Pew, it's a research organization, interviewed separate random samples of cell-only and landline telephone users and compared them on demographic, lifestyle, and attitudinal differences. Here are the results on the living situations for the two groups. Okay, so we see the two different samples from the two different populations obtained separately. And the living situation: parents, rent, own, live in a dorm, other, or refused to answer. Now, our hypotheses are still pretty much the same. We're doing this chi-square test for homogeneity. Okay? So the null is that they are homogeneous. They are from the same population. The distribution of living situation is the same in both populations. The alternative is this lack of homogeneity, meaning that the living situation distribution for the cell phone only population, it differs from that of the landline users. Okay? Is there a difference between the two? Now, we're still going to go through with an expected count, like we saw last week. We can also compare column percents and those observed versus expected values to isolate where those differences do occur. Let's take a look at what the output looks like. There's a big synopsis here. Let me just describe what we see in the GeoGebra output. Okay? So this is a 5x2 distribution in our dimensions. Okay? We have 5 breakdowns of the living arrangements, the 2 different samples from which we're pulling from, the landline and the cell. Remember that in this case, our white cells are what we input, they're what we observed. I have checked the boxes for the expected count and the chi-square contribution. So the expected count for the landline users who live with their parents. We expected about 136 across our entire sample. We got 165. For the cell phone users, we expected about 54 of them to live with their parents. We got 25. Okay? Those have a difference to them, and that kind of goes along with that chi-square contribution. Okay? Jump down here, we see our chi-square test statistic 61.2686. So each of these cells in the table will have their chi-square contribution, observed minus expected squared over expected. We get 6 of those points from the landline with their parents, 15.4 of those from the cell phone with their parents. All of those are adding up to 61. So if we see something that's a significant contribution, like this is a big discrepancy, this is a pretty big discrepancy, these two right here are not, in terms of those who live on their own, whether they have a landline or a cell phone only. Okay? Doesn't look like much of a difference there from what we would expect. A little bit down here with the dorm and the cell phone only. Okay, but we see major contributions here, here, and here to that overall chi-square test statistic. This corresponds with a p-value that is essentially 0. Okay? Reject the null, accept the alternative hypothesis that these two come from different populations. They are not homogeneous. That's what we have as our conclusion. The association between living situation and type of telephone service is statistically significant. These young adults accessible by landline phone are more likely to live with their parents and less likely to rent or live in a dorm. We saw that from the differences and from the chi-square contribution. Now, kind of interestingly enough, Pew wasn't just interested in their living situations, they were also looking at their values and beliefs and attitudes, they said. They found that young adults with landlines tend to be more likely to attend religious services at least once a week, and less likely to report drinking alcohol in the past 7 days, or to say that it is okay for people to smoke marijuana. They also tend to be less technologically savvy, using email, texting, visiting social networking sites less frequently. I will say that this survey is about 8 years old, so it's a little bit dated. Because of the rapid increase in cell-only users, plus the differences in a number of dimensions between cell-only users and their landline peers, most survey organizations now routinely include a cell-only sample when conducting a survey. And this issue of cell-only users has become more significant in those 8 years or so since this was originally done. Any questions on that one? So, big differences here. Chi-square test for independence. You're taking things from a single sample.
That's so unfortunate.
You guys at home, you still there? They don't speak up anyway, so I wouldn't know the difference. Of course, this is the lesson I record. Right? Somebody at home, give me a sign of life, a contribution, hey, you are here. Thank you. Thank you. We had a power failure, and I didn't know if it was just... So they can hear my sarcastic comments. All right, give me 1 sec to get going again. Okay. Now, I showed you this screen on Thursday during our last class period to look at the distribution for chi-square. We said that unlike the other distributions we've seen, z and t, this one is not symmetric. This is not a bell curve. Instead, it is heavily skewed to the right. So we have the bulk of our data down here on the lower end, and then this tail pulls out to the right. Now, degrees of freedom. Usually the calculator or GeoGebra will perform that calculation for you. There might be a case where you need to do this by hand. It's easy. Okay. However many breakdowns we have in the row, take 1 away from that. Same with the column, subtract 1 away from that, and multiply those together. So in this previous example, we had a 5 by 2 table. Subtract 1, so 4 by 1, 4 times 1, we had 4 degrees of freedom. Now, across the x-axis, if you were to look at a chi-square distribution, okay, I do have this linked on my Canvas homepage, but I never want you to use it, okay, in case you're interested. We had a chi-square statistic of about 66, I think. So what that would mean, we're following this orangish-red curve, and all the way out here on the right, wherever we get to 66, that's where we draw our line. I'm just going to pretend it's 6. And anything to the right under the curve, that is our p-value. Okay. You can see how close to the x-axis that curve would be, meaning that makes sense why we had such a small p-value. All right, our last type of chi-square test is called a chi-square GOF, goodness of fit test. Now, this is less common than the other two that we've seen, but chi-square for independence is by far the most common. Okay, a little less common than that is the homogeneity. Goodness of fit, even less common. But what this does, rather than compare to a set of expected values, instead with a goodness of fit test, you are testing to see if the categorical variable has a specified distribution, meaning that the distribution of the values is something that is predefined. Okay? For example, we have, like, let's say 100 people in our sample. We would expect 25% to be this category, 10% to be this category, 15% to be this category, 35% to be this category. That's what our expectation is, a predefined distribution. We have our sample. It doesn't match that perfectly, but we want to see if it is a good fit for that predefined distribution. Now, this is just the mathematical background for it. You can see the calculation of chi-square is the same. This isn't terribly useful for you. We will have to give degrees of freedom by hand to the calculator, but it's easy. It's just n-1 here, or actually k-1 in this case. Okay, you'll see that in just a second. K is the possible outcome. So how many rows do you have on this table? Now, you have a set probability. That's what I had said in this example I'm talking about. Okay, 25% in this breakdown, 10% in this breakdown. You don't work in terms of percents. Instead, you work in terms of what that equates to as an expectation. For example, it says births are not evenly distributed across the days of the week. Fewer babies are born on Saturday and Sunday than other days, probably because doctors find weekend births inconvenient. Okay, so there's this theory out there that more babies are born on weekdays, Monday through Friday, as opposed to the weekend. Now, I have a little bit of recent experience with this. I guess this idea makes sense. Okay? Babies are going to come when they're going to come. However, there are some births that are planned inductions, they are planned C-sections, and the idea is that a doctor schedules that for a weekday to have their weekends free. Or the weekends they are just dealing with the babies that are coming on their own. So to test this, they took a sample, random sample of 140 births from local records and shows this distribution across the days of the week. So we see Sunday through Saturday, and in fact, our two lowest counts are on the weekend. Sunday's only 13, Saturday's only 15. We want to know if this data gives significant evidence that local births are not equally likely on all days of the week. So, our expectation here is the null hypothesis, that there is an even distribution across all 7 days. So, mathematically, they express this as probability 1 equals probability 2 equals P3, P4, P5, P6, P7. They are all 1/7. Okay? They give you a probability. Now, we need to turn that into an expected count. Remember, we had a sample size that was pretty convenient for this problem of 140 births. Okay? That 7 will divide into it very nicely. So our alternative hypothesis here is simply that this is not 1/7 on every single day. So, the way that we perform this chi-square goodness of fit test, it is a different selection on your calculator. On the 84 plus, you're going to select chi-square GOF. I will say that the older calculators, like I have an 83 plus that I got my freshman or sophomore year of high school, and it does not have chi-square GOF. It just has chi-square. Okay, so if you happen to have one of these dinosaurs like I do, okay, use GeoGebra instead, or borrow somebody's newer calculator. Rather than using the matrices like we saw for regular chi-square, this just uses the lists. So you type in the expected values, the observed values into L1. What is your expectation? So he said 1/7 for each day of the week. All that means is 140 divided by 7 in each of these. So 20 births we would expect on each day of the week. That is our predefined distribution. Now, on the calculator, here I said you do have to provide degrees of freedom by hand. Okay, so 7 days of the week, 7 minus 1 is 6. That's easy. GeoGebra is pretty easy. Okay, same thing. Give it the size, observed, and then you do the expected count. It comes up in both cases with your chi-square value 7.6, and that corresponds with a p-value of 0.2689. This is the first p-value that we've seen that is bigger than 0.05. Fail to reject the null hypothesis, meaning we believe the null is true. Okay? Meaning that we do not have any evidence of a predefined, or that this varies significantly away from our expectation of 20 births or 1/7 on each day of the week. Keep in mind the language for our conclusions. If it's greater than 0.05, we fail to reject the null hypothesis. We never technically accept the null hypothesis. And this goes along with our identification of possible error. And if you fail to reject the null hypothesis, you believe the null hypothesis is true. You're not saying 100% it's definitely true. You're saying that in our sample, we did not see the evidence to reject. And that means the possibility of a type 2 error. With the calculator, you will also see that chi-square contribution. Remember, all of those individual chi-square values add up to this overall, in this case, 7.6. I don't have it here so that you can scroll across, but on your calculator you could. We have this difference here between 13 and 20. That's a pretty big difference, and we see that with our chi-square contribution. Okay, 2.45 of the 7.6. On Monday, 23 versus 20, that's not much of a difference, and we only see the first decimal point, but it's 0.4. Not that much of a difference. So this is just showing a little bit about what happens if you're doing the count by hand. Again, each difference squared over the expected, that's where each of these values come from, and their sum gives you that 7.6. All right. Anybody have any questions with this? So we've got 3 tests, all chi-square. Chi-square for independence. You're testing a single sample, and you see the breakdown of the variables within that sample. And you're testing to see if they're independent within that group, if there's no relationship. As the null hypothesis, there is a relationship as the alternative. Chi-square test for homogeneity, you're taking 2 different samples from 2 different populations, and they have that same breakdown. And make sure that you're taking those samples separately from different populations. That is key there. Lastly, is chi-square goodness of fit. You have a predefined distribution of what the breakdown should be. In this example that we did, it was 1/7 for each of those. So we saw 20, 20, 20, 20, 20 for our expected values. It doesn't have to be the same for each. It could be like 25% for the first one, 10% for the second one, 15% for the third one, that type of thing. And you multiply that by the overall total to get those expected numbers, those expected counts. But there are 3 types of tests. Any questions here?